Hi, my name is Cameron Burke, and this video is going to help you figure out what is going on with base-mediated nucleophilic acyl substitution reactions. So, first things first, a lot of what you need to know to understand base-mediated nucleophilic acyl substitution is the general nucleophilic acyl substitution mechanism, consisting of two steps. The first is a nucleophilic acyl addition, and the second is an elimination. Earlier videos go into detail about nucleophilic addition and elimination, so feel free to go back and review those if you need to. These bullet points are going to be a lot easier to understand after you've actually seen a base-mediated substitution mechanism, so I'm going to wait to talk about them until later. One thing I want to briefly touch on right now, though, is a special new ability that hydroxides and alkoxides gain in a base-mediated nucleophilic acyl substitution. For once, hydroxides and alkoxides can actually be a leaving group, even though they're kind of negative molecules. This is because a base-catalyzed nucleophilic acyl substitution has a carbonyl group and an R group, along with the hydroxyl in the leaving group spot. Our carbonyl carbon is serving as an electrophile because it has both the double bonded O pulling away electrons, and it also has the hydroxyl group pulling away electrons. So even though our bonded hydroxyl is negative, if a free hydroxide ion comes along and it has all these spare electrons, then the electrophilic carbon is going to be way more into that than it is into the oxygen it's currently bonded to. And for this reason, hydroxide can finally act as a leaving group in a base-mediated nucleophilic acyl substitution. Here's the actual mechanism that occurs when the presence of a base is driving a nucleophilic acyl substitution. Step 1 is a nucleophilic addition to the carbonyl carbon. The electrophilic carbonyl carbon is going to draw the attention of the electrons in this nucleophilic alkoxide, and they're going to swoop in on the carbonyl carbon. Once the carbonyl carbon finds an outside electron source, it doesn't need to share as much with its electron-hogging carbonyl oxygen anymore. So carbon lets the oxygen have those electrons, and a brand new structure is created. Our new structure is a tetrahedral intermediate. Our carbonyl oxygen's carrying too many electrons now. So this molecule can't really continue existing this way, it's just temporary. So oxygen alleviates this negative charge by reforming the bond with the carbonyl carbon. And the carbonyl carbon accommodates the reformed carbonyl bond by breaking the bond with its hydroxyl group. The hydroxyl group is the star of step 2 of our two-step mechanism, because step 2 is an elimination. Once it's free from the shackles of the carbonyl carbon, our hydroxyl ion just goes away, and the carbonyl carbon is once again double bonded to its carbonyl oxygen, and our hydroxide leaving group has been replaced with an alkoxide. Now that we've seen the actual mechanism that occurs when you have a base that's driving a nucleophilic acyl substitution, we can revisit these bullet points. The general mechanism of a nucleophilic acyl substitution is a two-step process, consisting of a nucleophilic addition and an elimination. In the first step, the negatively charged nucleophile attacks the electrophilic carbonyl carbon, causing carbon to break its bond and push electrons onto the carbonyl oxygen, creating a tetrahedral intermediate. But the intermediate doesn't last long, because in the second step, the carbonyl double bond reforms, and carbon tells the hydroxyl leaving group to get lost, completing the elimination and leaving behind the alkoxide in its place. Remember, when you're dealing with a base-mediated nucleophilic acyl substitution, only electrons and negative charges matter. Positive charges matter in an acid-mediated nucleophilic reaction, but that is going to be covered in a later video, so don't worry about it right now. What you worry about right now is that if you see a base driving your mechanism, follow the electrons. Thanks for watching!